Welcome to today's lecture. We will continue our discussion on the in situ non-destructive analysis, microanalysis of fluid inclusions. Today we will discuss on some of the other techniques which are also adopted by scientists across many different laboratories in the world. To begin with, there is another this particular technique. So, we will go to the from non-destructive to destructive technique. So destructive technique essentially is that the inclusion content is taken out, the inclusion is destroyed. So, one such in situ destructive analytical technique is the laser ablation ICP-MS. It is inductively coupled plasma mass spectrometer. We have already discussed the working principle in very brief about how a inductively coupled plasma mass spectrometer works. It works with a bringing into the material into a plasma state and then in ionic state, and the ions are actually carried or guided through some lenses, focused through some lenses which are essentially by applying proper current and voltage through the cones and then through the ion lenses in particular, and then they are guided through a quadrupole which are essentially 4 rods which the alternating rods are having RF and the DC fields, and appropriate combination will make the specific ions based on their mass by charge by mass ratio to be guided through to be detected by detector. So, here the technique is used for fluid inclusions with a variation that it is actually, so it is essentially called as dry analysis, because the inclusion content is for example, if there is a wafer and on this wafer there is an inclusion which is here at a depth of some microns, and then this is the laser. So, in a closed chamber in absence of any other gases, in a closed chamber again laser with a this laser is different from the laser which is used in LRM. This is pulse laser, much higher in its energy, excimer kind of laser or ND YAG, neodymium, yttrium, aluminum, garnet kind of laser which are much higher in energy, and this particular laser beam of a particular spot size, suppose this particular inclusion is measuring in some 20 micron or so, and so what will happen is, as and when this laser keeps on hitting the surface, the material here will be the material here, because of the very high temperature, the very high energy laser which is falling, which will be generating lots of high temperature, it will essentially ablate or evaporate the material which will be just above the host mineral, which is just above the inclusion, and with continued hitting of that laser pulse laser on this particular spot, it will ultimately reach the inclusion, and by increasing the beam diameter of this particular laser. So, what we will get? We will get the entire this content to be taken out, and essentially what will happen is that initially this thing which was a surface of the wafer, it will create a kind of a hole or a crater, because most of the inclusion content, and once the solid host was the solid host here is ablated, and the liquid part will very easily be ablated. Whatever is there, liquid and gas, will always be converted into or will be evaporated, nebulized, and then it will be with the help of the carrier gas. So, as it is written here, the analyte is the fluid inclusion. So, this fluid inclusion which is situated in a solid mineral host and at a particular depth from the surface is gradually ablated, and this material is carried by this carrier gas, and then rest of the things is similar to what happens in in an ICP-MS. So, it goes to the analyte goes to laser ablation, it is ablated, and then with the carrier gas then it comes to the plasma where it is converted to its ionic state, and then the ion focusing and the quadrupole and the detector. So, the only difference here is that when we have any particular solid surface like a mineral is being ablated for the analysis, the mineral will for a longer period of time, whatever is being ablated or is taken by the carrier gas will be the same, whereas in case of fluid inclusion it will only be for a very short time that the content of the inclusion will actually be going to the detector, and what we get there. So, the essential requirement is that the laser frequency and power should be appropriate for ablating the host mineral. The energy is of the order of 10 to 20 joules per centimeter square, and the laser optical system must have high magnification, because these inclusions are tiny in terms of tens of microns or even sometimes less than 10 micron. So, if we want to put the laser spot exactly on the inclusion, then we should be able to view the inclusion properly. So, the microscope system which is coupled to the laser ablation should have the proper magnification. So, laser optical system must have the high magnification objective to view fluid inclusions, and laser beam diameter variable as per the size of the inclusion be ablated. That because initially we start with a smaller diameter size of the laser to the laser spot and then increase it to, so that we would be getting the entire content of the inclusion to be ablated and analyzed. Now, microthermometric data should be available for this aqueous inclusion to be analyzed. Here the situation is that it is possible that we analyze the electrolytes in terms of the chlorides of the dominant cations like sodium, potassium, calcium, magnesium, iron and so on. Those are much more easily analyzed, because in this system there is the possibility that analyzing chlorine, which would be requiring much higher the ionization potential is far more higher. So, even though it is not impossible to analyze, but it is far more easier to analyze these cations rather than the anions. So, the microthermometric data should be available, because prior microthermometric data where the salinity in wet percent equivalent should be available. Why is it here? It is mentioned. So, this diagram is a typical spectra which is obtained by laser ablation of fluid inclusion. Here the intensity is plotted against time. So, you could see time in seconds from 10 to 110 seconds, and what you could see here that from beginning up to another 20 seconds or so, we are seeing that this is the silicon peak which is being showing here, silicon 29, and the time that is taken for the host mineral to get ablated and the inclusion cavity is exposed to the laser beam, and the ablation starts here, and then we see. So, these are the different steps in which the laser beam. So, initially it is a 20 micron beam, it is a 40 micron beam up to 60, and as the laser spot size is increased. So, we are getting higher and higher signals of this elemental species. We could see the chlorine 35 still can be analyzed, and here the different elements peaks are shown here. For example, this is tungsten, chlorine, this iron, sodium peak we could see here, sodium 23, and this is only the time that we have that the peak it is actually taken from, because there is no laser ablation data on fluid inclusion that has been generated in house, and these are as per the reference given here. So, this gives us a typically an idea actually what happens in a laser ablation kind of destructive analysis. So, and after the inclusion cavity is all exhausted, then again it comes back to the same host mineral spectra that would be expecting. So, this kind of a, so it is very transient the signals are transient. So, it needs very the data reduction has to be done in a very elaborate way, which I will not be discussing here much, but what essentially we get is, suppose, so the is abundance ratio of the two elemental species from this kind of spectra on a LAICP-MS. So, this can be expressed only in terms of that the concentration of X and concentration of Y in the inclusion will be a ratio of this concentration of X and concentration of Y in the standard, intensity of Y or intensity of X in the standard, and intensity of X and intensity of Y in the inclusion. Now, to convert to this relative abundance to absolute concentration, an independent estimate is needed, and that is coming from the fluid inclusion microthermometry. So, till so far, I mean till recently, the LAICP-MS analysis, to convert it to actual concentration in the inclusion species, it is always essential that it should be the prior microthermometric data is available and some value for this weight percent NaCl equivalent, that means in a way the sodium concentration is known. As you remember, when we were discussing about the ion chromatography and technique, and then we showed some relationship between what is exactly the total sodium chloride weight percent equivalent that is contributed by sodium, then 1.5 of magnesium and 1.5 of calcium and so on. So, some such kind of a standardization procedure has to be applied here, and so that a sodium concentration can be obtained, and that sodium concentration can be used as an internal standard and the analysis to be done. So, that is the kind of what is happening at the right at this point of time till recently, that there are some select, and these kind of facilities are there in many places, and there are fluid inclusionists who work specifically to understand the ore forming process, so that the concentration of different metallic species sometimes, like for example, is shown here tungsten, iron, and this example actually is taken from the mole granite. Again, I will come back to the same mole granite example which we discussed in context of the application to ore deposits. If you remember, we were talking about a situation where in the mole granite in the New England batholith in eastern Australia is a classic example of mineralization of tin, tungsten and base metal, where we compare this. This is the map in which the this part which is was shown without any hatching is basically the mole granite, and these are the metasedimentary country rock with some other granitic members present, and the mineral deposit distributions are like this, with the white circles are all tungsten dominated, then these diamond are tin, and in the periphery we see that the lead and zinc copper sulphide deposits. And if we just to recapitulate, then from fluid inclusion microthermometric data, from the salinity and temperature data, the authors way back, this is taken from old literature of the early 80s, which is the reference which I gave before. So, from fluid inclusion data itself, the inclusions in topaz in the early phase of magmatic fluid where there was boiling, and then the complex pegmatite, and then the tin quartz cassiterite vein in unaltered granite, and then giving rise to quartz cassiterite vein in altered granite, and then finally the lead and zinc sulphide deposits. So, that gave us a very good idea about the way the fluid evolved in space and time, with after the waning phase of the magmatic fluid activity, with the boiling of the fluid after the boiling one down. So, then only it gave rise to the scope for the meteoric fluid to mix with it, and it finally ended up with a low temperature situation, low temperature low salinity situation when the sulphides deposited. So, here the same mole granite example, mole granite was the mineralization was subjected to this LAICP-MS study as shown in the reference before. So, this is one example of one particular section taken from a quartz cassiterite vein, where the quartz, this is, you could see this is a polished section of the quartz, where the different generations of the trail bound inclusions are shown, and it has got about 3 to 4 growth zones. And when the several such generations of the trail bound inclusions, which are supposed to be preserving the fluid characteristics in the complex path of evolution, starting from very high salinity, very high temperature, where the temperature and salinity from the fluid inclusion studies are also shown on the top here, starting from 600 700 degrees Celsius temperature to going down to 200 degrees Celsius temperature in this spectrum. And these particular inclusions of different generations were subjected to this LA-ICP-MS analysis, where you could see the potassium, manganese, silver, tungsten, tin, boron, copper and arsenic. These are the species which were analyzed, and we could clearly see that there are conditions, or because the temperature and the salinity kind of situation in which most of the metals were held in solution, they were transporting, and there were domains after the mixing, or the temperature and salinity values decreased, the fluid mixed with the meteoric fluid, and then the deposition of the metals took place, where the fluid inclusions show very decreasing concentration of such kind of metals. So, it is a notable, the conformity of the inclusion chemistry with inferred path of evolution of the fluid mixing is quite notable here. And here it is a, so this is the reason why I chose this as a case study to be shown here, where there is a perfect agreement between what is actually inferred from a microthermometric data and the fluid evolution, and then when the inclusions were analyzed by a destructive in situ method like laser ablation ICP-MS, we get similar kind of picture. These days it is also possible, I mean this is just one such example, there are many such case studies of application of this technique into many ore deposits, where inclusions are ablated and analyzed from the ore minerals as well as the silicate gangue associated with them, and the difference in the fluid characteristics is also brought out, and many very important conclusions are arrived at by such kind of studies. So, there is no denying the fact that the in situ or the analysis of the inclusions need to be followed up after the fluid inclusion microthermometric data and microthermometric exercise to get better idea about the fluid characteristics, the fluid chemistry, evolution and so on. We will talk about again a method which is non-destructive, which is a method which is essentially the synchrotron source X-ray fluorescence, or it is also said as synchrotron radiation X-ray fluorescence, and it is it's mentioned as SR, XRF or SS, it does not matter, but actually it is come from the synchrotrons. We all know that they can be only called as international facility, because they are particle accelerator, and in order, if you want to, if anyone wants to know more exactly how exactly the synchrotron works, this link I am providing here. There could be many such sources of knowledge in public domain about the synchrotron. They are essentially accelerators in which this electron, which are generated from a particular source, are made to move in a closed space at velocities almost equal to the velocity of light, and in that process gaining energy in the magnitude of the giga electron volt. And when this particular so the electron which keeps on accelerating in a closed space in a ring kind of thing of stainless steel, so these electron, they emit light intensity, almost a very high intensity of light, and by using a proper magnetic field, these particular radiations this can be deflected and can be depending on the requirement. So, they are essentially sources of high intensity electromagnetic energy. We can choose the exactly wavelength range that we want. So, for example, we know that an X-ray range will be a very suitable range for analysis of elements, as we know conventionally by X-ray fluorescence techniques which we use for in conventional X-ray, where the X-ray is generated by an X-ray tube like a tungsten source, or we all know in a energy which is almost about 4 kilowatt or so, but compared to that this is a far more high energy system, and that is why there are possibly very limited number of known facilities all over the world in different parts of the country, different parts of the world. So, this should, if we basically select the particular light of the particular wavelength which is in the X-ray range, can guide them. So, in a particular synchrotron, some such multiple points on which this high energy or the electromagnetic radiations can be deflected, and can for multiple such stations which are essentially the laboratories in which these rays could be utilized for various types of studies. They are very routinely used by physicists for study of material structure and so on, but this could also be used for analyzing the fluid inclusions. Some such results are reported, although very few in number in literature. So, till recently nearly 30% uncertainty in results when tried with. So, there are some work which were essentially tried by taking some synthetic fluid inclusions with known concentration and then see how these signals are coming, and this particular technique has a lot of I would say promise for addressing issues of the fluid, ore fluid, the concentration of the ore metals in different evolutionary path of fluid in any kind of a mineralizing system, like say orogenic gold deposit system, or a magmatic or a porphyry copper system where they actually could be utilized. But then till so far the analytical protocol has not been very successful. When it was tried with synthetic fluid inclusions for analysis of strontium, it was observed that about the detection limit was about almost 2000 ppm, and whenever the, and then another problem is that the elements up to aluminum analyzing them is not is almost impossible. It is not so far been achieved with high precision, and elements from silicon onwards could be analyzed with better precision. And the another situation is that since many host minerals will also fluoresce to the X-ray, the choice so far has been restricted to quartz, and but then definitely more research will definitely make it suitable for other materials as well. The inclusion size, shape, and the depth of occurrence are important considerations with respect to the diameter of the beam of the X-ray. The diameter of the beam of the X-ray can be variable depending on the inclusion size that one wants to analyze. So, exactly the same, like the fluid inclusion wafer could be taken as the sample on which it could be exposed to the synchrotron source X-ray, and then the fluorescence could be studied by using appropriate detector. This is one example of a spectra obtained from a synchrotron source X-ray fluorescence. This is X-ray energy in kilo electron volt is given, and we could see that this solid line is from the inclusion and the dotted line is for the source for the host mineral, where you could see the silicon peak is coinciding. So, it gives us the idea that yes, this analytical process is actually is consistent, and then we could see that some of the signals of the elements like iron, manganese, copper, zinc, lead have much higher corresponding to what the signal is obtained from the host mineral, giving us an idea that this could be a very effective technique of analyzing, or for example, in some of the cases where we have we still debate on which fluid actually was carrying the gold, as we discussed before in case of the orogenic gold deposit, we still debate about the actual source, or even in case of multiple sources of the ore fluid. So, if they could be analyzed by the inclusions of that particular generation could be selected, or those particular samples which represent discrete sources of this particular fluid, such inclusions could be analyzed to confirm their ore bearing potentials. So, this is a typical synchrotron source X-ray fluorescence spectra. So, this method looks quite promising, and it addresses to address outstanding issues of ore fluid, and we expect to see more on this particular technique in the future. So, these are some of the techniques which are currently in practice for analysis of inclusion, essentially with an objective of augmenting the data that we generate by our microthermometric experiments. So, just a quick review that microthermometry is still the backbone, is still the technique which will give us the bulk of the data on fluid inclusions and the most important data on the fluid inclusions, because as far as the thermal regime is concerned, whether the wood fluid was of what kind of temperature range, high, low, from that we speculate whether the fluid could be metamorphic fluid, magmatic fluid, cornet fluid or meteoric fluid and so on. Here it would be worthwhile to make a mention about a recent development. It is already of course more than about a 1.5 decade and old or more. So, when we are experimenting or when we are doing the microthermometric study in conventional heating freezing stages, we are conducting the experiments in 1 atmosphere condition. That is the reason why all these problems of decrypitation of inclusions and so on, the problem we have not been able to overcome. But then recently there has been a development of a particular kind of hot stage, which is basically the hydrothermal diamond anvil apparatus. This HDAC, this hydrothermal diamond anvil apparatus, has been a very significant development in the recent past, in which it is possible to conduct microthermometric experiments at pressures more than 1 bar. So, that even if depending on the what kind of pressure which will be able to generate there, we will be able to succeed in getting the homogenization temperature of in most of the cases like the aqueous carbonic inclusions, where the inclusions decrypited because of building up of high internal pressure. And we expect to see a more wider use of this hydrothermal diamond anvil cell, which has come as a very significant improvement to the microthermometric experiments. And so, microthermometry is still the most dependable, and it gives us the first hand information about the fluid characteristics. But then microthermometric data should be augmented by data generated from bulk destructive analysis, like what we have given in the situation in very simple analytical method like ion chromatography, which is the instrumentation is simple, and the working principle and the handling of the equipment etc. will always make it as a choiceable technique for any fluid inclusionist. And only if we could somehow overcome the problem of the multiple generations of inclusions, or keeping in mind the uncertainties that kind of we are introducing, and situations corresponding to low temperature epithermal environment in which see these inclusions which are not subjected to much of later re-equilibration or later disturbances. Ion chromatographic method could be a very efficient technique to understand or to further characterize the inclusion fluid in terms of their concentration of different cationic species. And we would also like to see, because till so far we can so only problem is that in this kind of analysis we have we cannot get the entire range of cations analyzed by using one particular stationary phase which is present in their column. For example, if we want to analyze copper kind of base metal, different type of a detector is required, or if we want to go for the transition metals, different type of a column is required for the stationary phase. And but then they are still within the they still could be achieved without much of problem in a laboratory to generate such kind of bulk destructive analytical data like in what is possible in an ion chromatograph. So, laser Raman microspectrometry stands as the most easily adoptable and accessible technique for in situ non destructive analysis, and is very widely used, and we hope to see further improvement on this particular technique, and including the cryo Raman, which could also be practiced with far more commonly than what it is being done now. So, with this we conclude our discussion on the analysis of fluid inclusions, covering techniques of bulk destructive in situ destructive and in situ non destructive techniques. They have come of age to have to produce better quality of data, better science, while addressing the issues of the fluid, its origin, its role in processes that we are interested in. Thank you.